Okay, I won't use those words now that it's recording. But anyway, so just a quick reminder, and then we'll do a quick Python, and then we'll switch over to this, and then we'll be able to get you guys out for your lunch period. Since your last professor was rude and kept you late, I'll probably be able to let you go early. So first off, this business with the Runge Kutta methods, they're based on using, I know I went through the really quickly, but I just wanted to say that it's not just something that we made up, that actually they're based in reality, that you have this Taylor series expansion using 2 variables instead of 1. So the Taylor series methods, you're just expanding based on a single variable, the t or the x. But now we have 2 variables that we're thinking about an expansion, and it makes for a more accurate situation, but it's super complicated, at least the derivation. But once you've got it derived, we're just going to take a look at 2 of those methods. One of them, the one that we did on Friday, we'll do again today, and then we'll do another of the Runge Kutta methods next week after we deal with this thing here. So let me just remind you what this Runge Kutta method, I think it's actually called the Runge Kutta method of order 2. I think order 1 is the same as Euler's method, kind of like the most basic of any method. So I'd have to look it up to make sure that I'm right about that. But the important thing is that this one's called the midpoint method. It's called the Runge Kutta method. So this is the midpoint. So it's easier to think of it as the midpoint method. Unfortunately, we have a midpoint rule already. So you can think of it however you want. But when we get to the test and when we get to the coding, we'll use both of those, but mainly focus on midpoint. So I'll show you this in a bit and explain what that is. Okay, so the midpoint method, I just want to remind you what this is. We have this point right here, y of 0 is equal to 1. And so just to a quick reminder of how this works is you start off, you compute the slope. So this here, we'll do this in blue, that's going to be the slope at the point 0, 1. So that's your starting move. And then what you're going to do is you're going to go ahead, not a full step. So let's see, this is going to be our step size here. So that's going to be h, whatever h is. In this case, h is 1/2, but don't worry about that. So we go forward only halfway. So we take a half step, hence the name midpoint. So we take a half step. So conceptually, this is actually quite simple. You go forward just a half step. And so here's a half step right here, h over 2. And you compute a new slope at that new point. So you've got this new point here, and you say, well, what's the slope there? And the slope is probably not going to be exactly the same as it was before, but it's probably going to be close. So you're like, well, it's probably like this. Let's just pretend. Probably isn't, but whatever. So this is the slope at the midpoint. And so here's the key to this midpoint rule is you've got this slope, and you're like, okay, I'm going to use that one instead of this one, but everything else will be just like Euler's method. That's it. That's all we got to do. So here's how this works is we take that slope and you copy it down here, and then this is going to be the new point. Whoops, there. So there, that is the new point. So it's a little more complicated, but this midpoint rule, thinking of it as the midpoint, I want to go for this step here, but instead I'm going to go halfway and then reevaluate like what's going on with the slope, and then I'll go back and then I'll adjust my direction based on this, because it kind of stands to reason that if when you go halfway you get a slightly lower slope, then probably if I continued all the way on this blue line, I'm going to be off by a bit. So this allows us to correct a little bit, and it turns out that the correction is quite good. It changes you from having a order H, order H. Big O of H is the Euler's method. This method's big O of H cubed. So it's way better. So you get much closer. So anyway, that's conceptually. Now we'll just code this. It's really not difficult to code. Essentially what I'm going to do is I'm going to take Euler's method and I'm going to just redo Euler's method with this minor change. Instead of using the original slope, I'm going to use this slope, and that's it. So anyway, it's going to take a minute though, because we're going to retype it. Well, you can cut and paste if you want. Maybe I should show you where to cut and paste, just a sec. So I've got things set up here. Oh, wait, where is my stuff? There is my stuff. Okay, so I notice it's totally blank. Hold on a minute. Taylor method? Yeah. Here, I'll show you what I mean by cut and paste. There we go. Oh, it's little now, just a minute. Make this big. Hold on a minute. This is what we did on Friday, I think, here. We did the, oh yeah, I've already updated it. This is similar to what we did Friday. So that's what this is. It's not, yeah, I wonder if I can find what we actually did Friday. Just a sec. Let me zoom out. Open up. Open. Let's see, class Taylor methods. That's the one we did. This is the actual stuff that we did Friday. Does this look familiar? Yeah, that look, yeah. Okay, so the one that I want is Euler's method. So yeah, let's do this, you know, because no one likes to type. Okay, so here I'll copy this stuff. Come on, there it is. So if you happen to have, don't worry, I'll slow down. I won't leave you in the dust. But if you happen to have the stuff we did Friday, then or whatever day it was, maybe it's Wednesday, whenever we did the Taylor methods, if you have those, then you're in good shape, because then you can just copy that. I'm going to paste it over here, and then this is what we'll use. So let's see, make this one big. That's better. So this is just, whoa, this is just what we did Friday. Get rid of this. Sorry, I've got Chrome on one window and Firefox on the other for a variety of reasons, but let's see. This where Runge Kutta there. Okay, I've got it. Okay, so anyway, here's how I'm going to do this. Is the main difference? I'm going to rename this. Oh, we should probably start by import from math from math import everything. There we go. I was realizing, by the way, I should say, a little confession, is I've turned off all my AI, but I'm kind of looking forward to the end of the semester and turning it all back on because like I'm Googling a lot, like how do I do this and how do I do that? And it might be nice to just have it sort of auto-populate, but anyway, for now though, I appreciate you humoring me, and I'm trying to do it myself without using the AI tools, and I've been relatively successful. So anyway, the main thing that we're going to change is we're going to change this name, of course, to Runge Kutta 1. So it's the first of the Runge Kutta methods, the midpoint method. So this is Runge Kutta method. In parentheses, this is the midpoint. It's just that I don't want to use midpoint because we already have a midpoint rule. So that's why I'm going to call it Runge Kutta 1 for solving. Okay, this looks good. Yeah, everything else is good. So anyway, if you start off with this as your basis, everything else is going to be the same. The only thing we're going to change is down when we do the calculation. So when we do this calculation, instead of using the blue slope, which is the Euler's method, we're going to use the pink slope, which is the Runge Kutta method. That's it. So we just have one thing to change. Let's see if we can change it. Go down here and find it. So if you didn't have all of this, really, you don't need to type in all of these comments. The main thing is the stuff that is not commented. Here's the place that we're going to have to do a little bit of a change. Okay, so here's the deal, is the new slope. So here, that's the old slope. So that there, the one that's labeled slope, this is the slope. Here, I'll even do this, at xi comma yi. We could even just sort of specify. You don't have to, oh, yi. Come on. So you don't have to do the comment if you don't want to. I just wanted to be clear about what's happening. And now what I'm going to do is I'm going to make a new slope. The new slope is equal to the, let's see, And here, just to point out what's happening, you can see that brown point, that's the point that I'm interested in. So this midpoint, here I'll do this, that point is x0 plus h, and then y0 plus, oh, sorry, h over 2. H over 2 times the slope. So that's the coordinates of that point. So what I want to do is I want to move that far and then get a new slope. So check it out. Here's how this is going to work. There we go. We're going to do m is equal to f. So you might worry that we've already defined m right there. Don't worry. We're going to use that m and then redefine the m. It's fine. It's totally fine. Because once we use the m, we don't need it again, at least not in this particular Runge Kutta. There are some more advanced Runge Kutta methods where you do reuse the m, but we'll cross that bridge when we come to it. Okay, so here I'm just going to type in the coordinates of that point. That point is f of xi plus h over 2. And then this is the more complicated one, y of I plus h times m over 2. And this is going to be the slope at the midpoint. So just to show you again, I know it's going to be annoying, it's going to blink off and on, but just to remind you, here's the deal, is I just want to know this point, and this is the coordinates of that point, is the x plus h over 2, and then y plus h over 2 times m, and I've just written it as h times m over 2, just for simplicity. I thought it would be easier. I don't know. Maybe you like to, I'm always scared to write h over 2 times m, because I don't know where how it's going to be interpreted. So I always put the slash at the end. Okay, so there it is. Now the rest of this is pretty much just yeah, I don't have to change anything else, because that's good. That's all good. Yeah, we're all done. So let's try it out. Oh, I need a function, don't I? I guess I need to go back one more time. Sorry about this. So this is, oh, you can't see it very well. It's okay. I need a function. So we're going to do this one. You can't see it. It's the one that we did last time. Here, I'll zoom in so you can see it. That one, that differential equation, is that the one that I have on my, oh, I have a different one. It's okay. We'll use this one. We can do this one as well. So this is supposedly the one that we did last time. So copy that. We'll paste it in over here. There we go. And then we will do the test. And I'm so lazy. I'm just going to do the, watch this. I'm going to do exactly the same test that I did over here. Here we go. Copy. And then paste it in here. And I just have to change from Taylor to Runge Kutta. So Runge Kutta. So I guess I need to change all of these. There's probably a way to global replace, but I'm not cool enough for that. Let's change these. There. Yeah, I think all the rest is good. I don't think I need to change anything else. Guess we're going to find out. See if it works. Oh no, what happened? Too many sessions. I've got too much going on. Let's shut this one down just a minute. Let's see, can I just shut this one down? Sure. Okay, now can I do this? Sorry, I had too much going on apparently. Didn't like it, did I? Maximum of 3 things. Yeah, I found that whenever I look at your stuff, I have to be careful because I have like 5 open at once or something. Okay, so there it is. Those are the Runge Kutta method. I think the correct answer is 3.75, and you can see how quickly, even at n equals 10, we're right on top of the correct answer, 3.75. And we can compare that to the Taylor method of order 1, which was terrible, you didn't even get to, I mean, you're not even, with 100, you're not even that close. And then with Taylor method of order 2, where's Taylor method of order 2? It's here somewhere, isn't it? Oh yeah, here it is. Okay, that's not bad. Taylor method of order 2 looks like it's almost as good, but still not quite as good. Oh yeah, my n equals 2. I need to change to 10 there. But um, yeah, so it looks like this is even better than the Taylor method of order 2. I don't know where order 3 went. Oh, here's order 3. Looks like order 3 is, no, it's about the same as order 3. Yeah, it's about the same if you compare the order 3. Remember, the target is 3.75. So here you're good if you round 3.759. You're off by a little bit in the fourth digit. Here you're off by a little bit in the fourth digit. I guess you're slightly closer here. And then with n equals 100, 1, 2, 3, 4, 5, 6 digits. 1, 2, 3, 4, 5, 6, 7. Okay, so Runge Kutta 1 isn't as good as Taylor 3, but it's pretty close. So, and it seems like it's a lot less work. So there's that. All right, so let's just pause, see if you have any questions or concerns or anything. Yeah, what do you think? Uh-oh. Okay, so let's zoom out a bit here and make sure we're using the same. Okay, the function. Yeah, so if you have the same function we had last time. Anything else, other concerns? All right, so the other Runge Kutta methods, which we won't go over because we have some other things to deal with this week, we'll go over next week. Not to worry, we'll get into them a bit. They're sort of similar. So if you can imagine, you could take a half of a step, and then you could go back, and then you could take another half step using the new slope. You could do some correcting and maybe do a full step. So there are some, I think the order 2, the next Runge Kutta method, you're basically taking half a step, and then you take a full step, and then you go back and sort of average things together to get your, make the final the final step that you want, which is kind of interesting. But anyway, you can see it's pretty straightforward though. At least this one. The more complicated Runge Kutta methods are harder. Or anything else before we move on? Okay, so I was looking over your, I know you probably know I gave exams last week in my other classes, and I was realizing we need to do something for you, but we haven't been keeping up with quizzes. And so here's what I got is I have the practice exam. I actually wrote up an exam for you, and this is the exam I wrote up for you, but I just renamed it. I called it practice exam, and I thought that we could take some time to take a look at this and work through a couple of these today, a couple of them on Wednesday, and then have an actual exam that is just this simple on Friday. So this isn't a quiz or an exam, but you can treat it as such, as a quiz at least. So if you give me a minute here, I'll tell you what to start with. I know we're going to go out of order, even though here there's 2 pages there. It's a 2-page deal. I didn't do it on the tabloid paper because I wasn't quick enough with my files. Here's one more. Here you go. So we're not going to do this in the same order that they appear here, but we'll do, there we go. Now what I wanted to do is I wanted to do the one that we just did. I thought we could do, since it's sort of fresh in your mind. It's on the very back page. You'll find the number 8. So if you turn the whole thing over, and for those who are watching from home, don't fret. I do have papers here for you, and I will put this on the screen once I get it. So give me a sec. So anyway, take a look at number 8. Get started on that, and once I get myself set up, I'll give you a couple of pointers, because number 7 and 6 are similar to number 8 in terms of how you might want to solve this. Let's see. Exam 2, is this? Yes. There we go. There. Here's. Okay, so I know you're just getting started, but I thought that I'd point out a couple things about this that might help when you do this on the actual test and also when you do the practice test for me for Wednesday, because that's your main homework. I know I got to put together something for you to do for the Runge Kutta methods, but we'll do that for next week. So anyway, what I'd suggest you do with this one, as well as 7 and 6, is that what you're doing here is you're doing the same thing over and over again, of course. And so make a table and, just keep things sorted out. I was tempted to actually make that table for you, but I didn't want to make you feel like you had to fit into my way of thinking about this. But at least for me, it's really helpful if I make myself a table. Also, I didn't want to give away all of the answers. It's pretty straightforward. But so here's what I would do if I were to do this on a test. I might do something like this. You have t, you have y. And so we're starting off with t equals 0, y equals 1. And then we have to think through, what do we need to compute this particular method? Well, what we're going to need is we're going to need the function value at that point. So that's easy enough. Plug 0 and 1 in here, and I get -2. By the way, here's my plan, is I'm going to do this first line for you, and then you're going to try to do the rest of this particular problem. So if you're confused about where I just got that -2 or anything else I put up here, let me know. I think it's pretty obvious, but maybe not. Now at this point, here's where we might differ in what we think is necessary. And so I'll put down what I would put, if I was doing this on my table, but you can choose to put less than this or more than this. You have to show me what you're doing, but you don't have to make it quite as rigid as mine is. So then what I'm going to do is I'm going to do this. So t plus h over 2. Whoops, that's supposed to be a 2. Let me get rid of that. That's better. Whoops, not that. And then y plus h over 2 times f. So what I'm doing here, and like I said, this is a little bit maybe overkill in terms of making a table, but you got to compute these anyway. And so what this is I'm asking for that brown point. If you remember from my diagram, I'm saying, okay, if I take a half step, where will I be? This is the half step. This is the midpoint. So it's the stepping stone that we're going to use. And then after that, I'm going to do f of that thing, t plus h over 2, y plus h over 2 times f. And then, of course, once you have that, it should be pretty easy to get our next value for y. But we'll go through this. Let's just walk through this. So the first thing, this is pretty self-explanatory. T plus h over 2 is going to be h is 1/2. So that means that's 0.25. And then y plus 0.25 times this number here. So it'll be 1 plus 0.25 times negative 2. That's 1 plus negative 0.5. So let me just pause and make sure that you see where those numbers came from. So you're probably like, well, I don't have to write down all my work, but I mean, if it's like here, you can do most of this in your head, probably, or on a calculator, but show me the intermediate steps at least to show me that you're not just, I don't know, making up numbers. Okay, then my next line is I'm just going to pump that into my function. By the way, this here, that is the function. If you're not sure, maybe you're embarrassed to ask, don't be embarrassed. It's okay. But anyway, I'm going to pump those two numbers into that function there. So it's going to be 0.25 minus 1, which is negative 0.75. And then here we might differ again, is I'm just going to compute the next value of y and put it in here. But you might feel more comfortable maybe making another column for this, just to remind yourself of the formula. I mean, the formula is going to be, maybe I should put it down here. I'll do it. Yeah, there's not a lot of room. Just a minute. I think I have to get rid of all those lines. Yeah, yeah. There we go. Okay, so that one is going to be, so you've got the y new is equal to y old plus h, plus h times f of t plus h over 2, y plus h over 2 times f. So in other words, I'm going to take this column and use it to compute the new value of y. That's it. So this is going to be, I mean, I could do this here. It's 1 plus h is 1/2 times negative 0.75. So that's negative 0.375. So this is going to be 0.5625. I don't know if I can do the next line in my head. Probably going to need a calculator, so I'm going to pull one out. But see if you can do the next two steps, because that's what this is asking you to do. It says our goal is to get y of 1.5. And so here's how this is going to work. You're going to do it 2 more times. There's the first time, and then here's the second time. There. So this is the goal right here. So see how you do. And if you're confused, you can call me over. I'm going to go, oh, here's a calculator. Because I can't do this in my head at this point. You know, I guess if you're clever, you probably could get your calculator, using the table feature. I don't know if anyone's into that. I used to mess around with it that way, but it hardly seems worth it when we're just doing 3 lines. So we're just going to do this 3 times. If I was doing it 10 times, it would probably be more worth it. Okay. Yes.
So I see this is 0
Mm-hmm.
plus h over 2. I thought the h is given as 1
Yeah.
over 2.
So what's 1/2 divided by 2?
I think we get a 4.
1/4. Yeah. And so what's 0 plus 1/4?
Is it a 1/4 or 4?
What?
I'm
Okay.
confused.
H is 0.5.
Mhm.
What's half of 0.5?
I think we get a 4.
1/4. Yes, you get a fourth.
Yeah.
So what's 0 plus 1/4?
Okay. 0.25.
Yeah.
Okay, what you said.
Yeah.
This
Yeah,
is-
you're right. H is 1/2, and so h over 2 is 1/4, 0.25. So if you prefer using fractions, you can. They're going to get ugly. Like this is -3/4, and then you can get your next. So yeah, next one is going to be 1/2 for t. I guess that's what I have, and then 0.625, which is 5/8. So you could do fractions, but might as well use your calculator and get a decimal. Yeah, see if you can at least fill in this part of this next line so you can compare with what I have. So yeah, see if you can compute this, and then we'll go over it in just a minute. Here you go. Here, you can always use one of my calculators. Then it doesn't have that big bright line.
Yeah.
It's so annoying. There. So yeah, it's all pretty simple arithmetic. So you should be able to do it. Hey, 130. Okay. Okay. Sam. Yeah. There. You see how you're doing? You got, you can fill this stuff in, can't you?
Yeah,
Oh, you don't like mine?
No,
Oh.
it's
Go to, what are you doing?
it's I don't know.
Second quid.
Oh, okay. I
You
didn't
can't do
know.
that?
I've never used.
Okay.
It's too huge.
Yeah. It's so much better. So if you see Zane and Sam, I've got theirs, or if they're listening, I've got their versions of this document with their names on them. So, or they might not care. They can come by and get them. I'll go over this this next. I don't know. You might be done with the whole thing, but I'll go over the next one next. Just the 0.5 in just a minute. I'm gonna give Matthew another chance to acclimate to the new calculator. And if anyone else has questions, I can come help. Maybe I'll do the next level. Ooh. All right, well, let's see how we're doing. I know you're, did you get the, oh, you're working on, yeah, go ahead. So, yeah, getting used to a new calculator might be a problem, but let's go ahead and see how we're doing. I started the next line, but I started getting scared because of all the digits. So you can check the blue stuff first. If the pink stuff is wrong, don't, but I'm pretty sure the blue stuff is correct. So I got the function value when I plugged those two in, and then I got this for the t plus h over 2 and that, and then that gave me my new slope. So is the blue stuff, any problems with the blue? Yeah, it looks okay. I can double check. Yeah, this is where the Python is so much better than the, and this is also a good reason why on the actual test, you're gonna wanna write it all out so that you can show me, like if you make a mistake, where the mistake is. The last digit? Oh, in pink? Oh, we're not to pink yet. What, 93125? Which, so sorry, this one? That one's wrong? Let me see where we went wrong. Let's see, so it's the original y, 0.5625 plus 0.25 times this, negative 0.125. Oh, huh. I don't know where that came from. Yeah, you're right. I mean, we knew that you were right anyway, but let's see, get rid of all that. So 0.53125. There, that look better? Yeah, so good thing. Yeah, like I said, it's so many digits, I was getting scared. But then the rest of this, hopefully we can do this. This is going to be 1.25 minus 2 times that previous thing. So I got 0.18 7.5. Does that look good? Okay. So interesting that that if we were going with Euler's method, we'd have a negative slope. But after this correction, doing a little half step, you're like, wait a minute, the slope should be positive. There's a big difference actually, there's a big difference between the two blue ones as well. But it's just interesting to me that the correction goes from positive to negative. Okay, so then we'll get the last piece. The last piece is going to be the old y. So 0.5625 plus h over 2, which is 0.5, times that number there. So I've got 0.65625. Okay, 65625. Nice. Whew. Wow, that was rough. So anyway, this is good to know that this, because here's what I was thinking, and this I may revise by Wednesday. So remember, my goal is to get this out of the way on Friday. We'll have our test, but this way we can sort of collaborate on constructing the test. But my goal was to just take this and just change the f. So here's what I was thinking I would do. But now I think I need to change more than the f. I was just going to change this to 2t minus y instead of t minus 2y. Honestly, that's what my plan was. But now I'm thinking I also need to change this, maybe change this to y of 1 so that you only have to do 2 steps instead of like that third step got a little onerous, didn't it? So if you just had to do the green and the blue, I think that would be sufficient. So anyway, I was going to do something similar to the others. So I guess what we should do is try to do as much of this as you can before Wednesday. That way on Wednesday, you can tell me if it's too much. Like now I'll leave it like this for the practice test, but just to warn you, when we get to the actual test on Friday, I'm going to change these to y of 1 instead of y of 1.5. That way you only have to do 2 steps instead of 3. So this is Taylor method of order 2. So you're going to have to do the derivative. This is f. We're going to have to do f prime, which is going to be 1 minus 2y prime, which is 1 minus 2 times t minus 2y. So you'll have to do that. We'll talk about that more on Wednesday. Same thing goes with this one. Same deal. I don't know about, I think this is fine, but we'll talk about this on Wednesday. Once again, I'll be changing this slightly for the actual test. And then these other ones, we've done this so many times. I don't think you're going to have trouble with this. But I do have n equals 3. I don't think that's too much, but we'll find out because I'm going to have to do all of this for Wednesday as well. So hopefully this isn't too long. I guess that I'm on the heels of giving a test on Friday to my differential equations class where there was one problem that was truly horrible, right? Yeah. Anyway, I had several people leave and say that was awful. It was the last question. I'm hopefully going to do penance for that today. But anyway, so that's it. So does everyone understand what you're going to do for Friday for me? Is you're going to do this. Maybe I'll put this online for the 2 people who aren't here in case they just want to download it. If they don't want to have to track me down, I do have them with their names on them. But I'll take a minute, upload these, and then look at this. You have a few extra minutes to go get your bagel and then come back and play Super Mega Lucky Box. So let me pause the video so that